In this chapter, we begin studying the motion of objects. There are many ways objects can move. They can move at a constant speed. They can speed up, they can slow down, and they can move in complicated ways. Because motion involves an object moving from one position to another, we first need to understand the concept of position. Position is where an object is located at one point in time. An object can have many different positions, and motion is what gets it from one position to another. Obviously, there are many types of objects we can investigate, and you'll be expected to draw diagrams showing the motion under investigation. Now, if you are like me, you might not be the world's best artist. So in physics, we present any object as a simple dot. Let's look at the concept of position a little more closely with an example. You are waiting outside of the school and call a friend to come pick you up a block from the school. But there are many places that are a block from the school. And so, when your friend comes to pick you up, you get left behind. If you had described your position correctly, then your friend would know exactly where to pick you up. There are three conditions necessary to accurately describe an object's position. First, you need a reference point. In this example, the school is the reference point. Reference points need to be objects or locations that stay fixed at one place. Second, you need to specify the distance from that reference point. Although you are more familiar with inches, feet, and miles, most of the time in physics we will be using SI units for measurements. Third, you need to state the direction from the reference point. So these three bits of information, reference point, distance, and direction, are needed to describe an object's position. As we continue in this course, you will begin to see that direction is an important aspect when investigating motion. Direction is usually described according to a coordinate system, and you need to know about the three most common coordinate systems for describing motion. You should already be familiar with the Cartesian coordinate system from your studies in algebra and geometry. In this system, the horizontal axis is divided into the positive and negative x directions, and the vertical axis is divided into the positive and negative y directions. From your experience with maps, you should also be familiar with the cardinal coordinate system of north, south, east, and west. In this system, north and east are considered to be positive directions, and south and west are negative directions. Finally, there is the relative coordinate system of up, down, left, and right, in which up and right are positive, and down and left are negative. Now that you know how to accurately describe an object's position, let's move on to describing motion. Motion is defined as a change in an object's position over a certain time interval. One way to describe an object's motion is with a motion diagram. In a motion diagram, several snapshots are taken of an object as its position changes. Each snapshot occurs over the same interval of time. In these examples, we will be taking a snapshot every second. Now remember, we don't want to have to draw all of these diagrams. So instead, we will use a dot for each snapshot. It is also important to number the moments in time, beginning with 0. The skater pictured here is traveling at a constant speed. You can tell it is a constant speed because all of the dots are evenly spaced. This skater travels the same distance for each second in time. In this next example, a runner is speeding up. A motion diagram shows that each dot becomes further and further apart. Our final example shows a car slowing down. The motion diagram for this car shows dots that are getting closer and closer together. To summarize motion diagrams, objects moving at a constant speed have dots that are equally spaced apart, objects that are speeding up have dots that are further apart, and objects that are slowing down have dots that are closer together. Before we continue our discussion of motion, you need to understand the difference between distance and displacement. Distance is defined as the total length that an object travels during its entire path. The abbreviation for distance is the letter D. In physics, there will be measurements like distance which have a number associated with them but do not require direction. These types of measurements are called scalars, and the numbers are called magnitudes. Unlike distance, displacement is only the change in an object's position from the beginning to the end, regardless of the path it takes. This is the symbol for displacement, and it is pronounced delta x. If the displacement is in the vertical direction, then a y is substituted for the x. Remember how I said that direction is an important concept in physics? Measurements such as displacement, and there will be many of them, require a direction as well as the magnitude. These types of measurements are called vectors. Because displacement is our first introduction to vectors, let's break down what it really means. The triangle symbol in front of the x is the Greek letter delta, and in physics this symbol means change. When paired with the letter x, it means change in the horizontal position. We calculate this change using the following formula. Change in position equals final position minus initial position. Written with symbols, the equation looks like this. Here are a few examples of how delta is commonly used in physics. Now there may be times when you may see this equation written in some other form. You may even see me occasionally do it in class. But you need to be most familiar with the form of the equation that will be used on the AP equation sheet that you will have available to you for the AP test, and that is the one shown here. Calculating distance is different from calculating displacement, as these next few examples will show. In this first example, a car travels 2 miles along a horizontal path. The distance is simply how far the car has moved during the entire trip. Displacement is calculated by subtracting the initial position from the final position. In this case, the initial position is the starting point, which is assigned a value of 0, and the final position is 2 miles. This gives us a magnitude of displacement of 2 miles. To complete the calculation, we need to add a direction to the vector of displacement, and so the displacement is 2 miles to the right, or positive 2 miles. In this next example, a car travels the same 2 miles, but then turns around and comes back 1 mile. The distance traveled is thus 3 miles. However, the final position of the car is only 1 mile from the initial position, and so the displacement in this example is 1 mile to the right. In the third example, the car travels the original 2 miles, and then turns around and returns to the starting point. The distance traveled is 2 miles there and 2 miles back, for a total of 4 miles. The displacement is 0 because the final and initial positions are the same. Notice that when the magnitude is 0, the vector does not have any units attached to it. So far, our examples have looked at motion along a straight line. But what happens when the motion is along both the x and y axes? Here we have a car traveling east for 4 miles, and then north for 3 miles. Computing the distance is relatively simple. The total distance traveled is 7 miles. But what about the displacement? Displacement is only concerned with the starting and ending positions. So in this example, the displacement is the blue arrow. Hopefully, you recognize that we have drawn a right triangle, and we can use the Pythagorean theorem to find the displacement, which is the hypotenuse of this triangle. Using the Pythagorean theorem, we get a magnitude of displacement of 5 miles. Remember though, displacement is a vector, and it needs a direction. To find the direction of this displacement vector, we need to find this angle. That symbol is the Greek letter theta, and is used to indicate angles. To find the angle, you will need to apply trigonometry. In this case, we know that 3 miles is the opposite side, and 4 miles is the adjacent side, so we can use the tangent function of trigonometry. To solve for the angle theta, we need to take the tangent to the other side of the equation and change it to the inverse tangent. Solving on a calculator gives us an angle of 37 degrees. We can now state the displacement as 5 miles at 37 degrees north of east, or northeast. You will often hear me say, use the Pythagorean theorem inverse tangent, because this method will be used often in this class. We close out this chapter with a brief discussion about the difference between speed and velocity. You are already familiar with the differences between distance and displacement. Speed and velocity are much the same. Speed is a scalar, which only consists of magnitude, whereas velocity is a vector, which requires both magnitude and direction. The definition of speed is given here. Notice that distance is used in the definition. Here's the equation for speed. Sometimes the letter S is used for speed, but to be honest, this equation will not be used that often in physics. in the box are some of the more common units for speed: meters per second, kilometers per hour, and the one you are most familiar with, miles per hour. The definition for velocity shown here uses the word displacement instead of distance. The equation for velocity looks like this. If you were to read this equation out loud, it would sound like this. Velocity is equal to the change in position divided by the change in time, which is equal to the final position minus the initial position, all divided by time. The units for velocity are the same as the units for speed, but don't forget that velocity needs a direction. This concludes the video lecture for Chapter 1. Coming up next, we will begin exploring motion in one dimension in greater detail.